Hi all. In the last video, we saw the importance of designing drilling hydraulics for safe and efficient drilling operations. That designing drilling hydraulics involves three main factors. One is properly maintaining the hydrostatic pressure. The second thing is proper flow pattern, and the third thing is proper selection of the rheological properties of the fluids. So the flow patterns involves either laminar flow pattern or a turbulent flow based on a dimensionless number called Reynolds number. And the rheological properties or rheological classification of the fluids involve Newtonian fluid and non-Newtonian fluid. Non-Newtonian, especially, we are more concerned related to Bingham plastic model and the power law model. So in this video, we are going to see the laminar flow in pipes and annuli and turbulent flow pipes in annuli, and how during the laminar flow in pipes and annuli, the pressure drop due to friction losses is being calculated in pipes and annuli, both Newtonian and non-Newtonian fluid, and also the pressure loss calculated during the turbulent flow in pipes and annuli for both Newtonian and non-Newtonian fluid. So for Newtonian, for laminar flow for both Newtonian and non-Newtonian fluid, we can able to make closed form solutions by simplifying the geometry of the model, and also for simplifying the flow, physics, so that the momentum and mass conservation equations can be simplified, and which end up in closed form solutions for computing the pressure drop across the pipes and annuli. For Newtonian fluid model, for example, for flow through pipe, 4.26 gives you a closed form solution to compute the pressure drop across the particular segment of the flow pipe. And similarly, 4.27 gives you the shear rate by from through which the from the viscosity we can compute the shear stress. Similarly, for the annulus, 4.28 gives you the pressure drop across the annulus for a particular segment, and d to d one of the geometrical properties for the annulus, and mu is the average velocity profile for the particular annular flow in a laminar regime. So again, for a non-Newtonian side, both for pipe and annulus, especially for Bingham plastic fluid, 4.30 gives you the closed form solution for the calculating the frictional pressure loss across the pipe, and 4.32 gives you the frictional pressure loss across the annulus for the Bingham plastic, considering those rheological properties like yield point and the plastic viscosity. So mu here is similar to like a plastic viscosity, and these are the geometrical parameters as mentioned in the Newtonian flow model. Similarly, power law model, the parameters involved are n and k, flow behavior index, and k value, which is define the physics of how thick the viscosity of the fluid would be. So based on this k and this n, the more the k and the more the friction loss, it will give you this nonlinear formula based on that flow behavior index. And also this also gives you nonlinear relations between the frictional velocity and the pressure drop based on the behavior index. It can be from 0 to 1 as mentioned in the last lecture. And similar to the annulus, same thing, only the geometrical properties differ, and it's almost similar to that of the flow through pipe. So this mean velocity is plays a key role, because once the mean velocity exceeds a certain critical point, it ended up in a turbulent flow by through which these equations which we introduced earlier will not give you a proper calculation for the friction pressure loss. We will have a different calculation. We will coming to this later part of this video. So this critical velocity will determine what is laminar flow and turbulent flow. So for Brigham plastic fluid model for the pipe, this is the critical velocity calculations, which depends upon the rheological and geometrical properties. And for the flow through annulus, this is the critical velocity calculations equations. And similar to the power law fluid, this is a critical velocity calculation equation for the pipe, 4.40 and 4.41 for the annulus. So, considering the turbulent flow, as mentioned in the last video, there are a critical Reynolds number usually around 4000, where we ended up in a fully turbulent flow, for which we cannot able to utilize similar equations that we introduced earlier in the laminar for closed form solution, simplifying the equation, simplifying the physics, and simplifying the geometry to compute the pressure loss, which eventually we can do, but it won't give you the proper value. So there are some empirical experiments carried out during the industrials during around 50s and 60s, and by that they have ended up in like equation empirical relations like 4.42, and also a chart here based on the Reynolds number. We can ended up what are the frictions factor during the laminar and the turbulent regime. So for laminar flow, this is something like a closed form solution, 16 by NRE. For laminar, it will be a nonlinear relationship between the friction factor and the Reynolds number. So this is will be a nonlinear equations, which we can use an iterative technique like Newton-Raphson method to identify the friction factors, or I can either directly go to the chart like we mentioned in the figure 4.7 to compute the friction factor, provided we know the Reynolds number. But there can also be some certain simplifications for mostly drilling operation. Relative roughness can be neglected, or it can be assumed to be of a very low value, and which the equation 4.42 can be reduced to 4.43. But there are additional simplifications can be done, for which mostly the turbulent flow Reynolds number would be for drilling operations related to the pipe, especially for pipe can be between 2000 to 100,000, for which the friction factor can be have a non-relation between the Reynolds number and the F. So once the F is computed, we can use some empirical correlations to identify the frictional pressure drop using the 4.45. If you see that for laminar, it will be a linear relationship between the mean velocity and the pressure drop, but here there will be a quadratic relationship between the pressure for the even for the Newtonian model. For Bingham plastic model, the same thing can be applied 4.45. Only the thing is how we are computing the friction factor, what is going to be different between the Newtonian and the non-Newtonian model. For non-Newtonian model, as mentioned earlier, we need to compute Reynolds number, and we have also to determine the critical Reynolds number to determine whether it's a laminar or turbulent regime. So for computing the critical Reynolds number, it depends upon another dimensional number called Headstone number. The Headstone number and critical Reynolds number can be computed through iteratively by solving 4.47 and 4.48 simultaneously, or we can use this chart to compute the Headstone number to identify the critical Reynolds number. So once we identify the flow regime like laminar or turbulent based on this above equations and the chart, then we can compute the friction factor. Once the friction factor is computed using that 4.43, 4.45 like mentioned earlier, this can be utilized. Once the friction factor then can be substituted to compute the pressure drop across the bigger plastic fluid model. Similar case would be having for the power law fluid model, where we have some empirical friction factor correlations which involves flow behavior index, which is a rheological parameter. So we compute the Reynolds number using those rheological parameters. Once the Reynolds number is computed, we can compute the friction factors. Once the friction factors are computed, we can use again 4.45 to compute the pressure loss. So the this also can be have a specialized equations where we can compute the friction factor directly using this non-relationship once we know the Reynolds number, not necessary to depend upon 4.44, which will have a special equation 4.55 for especially for the formula fluid. Once these friction factors are computed, we can use again that standardized 4.45 equations which we introduced earlier for the Newtonian model to compute the pressure drop due to the frictional pressure loss. Hopefully in the next video we'll see about how the pressure drop across various connections, because connecting between these pipes are specialized flow through connections between the standpipe and Kelly's well all have a different geometrical configurations, which ultimately we don't have a closed-form solutions. Again, we have to depend upon empirical correlations to compute the pressure drop. Hopefully, we'll discuss this and also how we compute the pressure drop across the bit hydraulics that which have a nozzle effect for effective hole cleaning, which we'll be discussing in the next lecture. Thank you.